Hello to everybody and welcome to the fourth lecture of Heat and Mass Transfer MHM 42780. During the last three lectures, I covered chapter 12 of our prescribed textbook. I talked about radiative properties of surfaces, how radiation is distributed with wavelength, blackbody definition, and some other topics. In this lecture, I'm going to start with chapter 13 of our textbook, and I'm going to speak about radiation view factor. This chapter, compared to chapter 12, has a much stronger content in engineering because we want to find out, for instance, how much radiation leaves one surface that gets to another surface. So view factor is something important that allows us to make those kind of calculations. We can find something, we can calculate, which is very important for us. So first, let me define view factor. So view factor of surface I to j, we show it with f I j. We also can show it with I to j, and we can define it as the fraction of radiation leaving surface I that strikes surface J directly. Okay? So the fraction of radiation leaving surface I that strikes surface J directly, we call it view factor. View factor, and we show it with Fij or Fi2j. If you go to your textbook, you can find that there are tables like table 13.1, table 13.2, figure 13.5, 6, 7, and 8. In these figures, you can find that the view factor for some of the common geometries that we are facing in this chapter, as well as like equations. So very simple geometries, you can just like simply go to the table and you can find and calculate it. But the problem is, those are for very simple geometries and standard ones. In reality, most of the times we are facing with geometries that they are not standard, and we need to find the view factor based on these standard geometries. Okay? So in order to be able to find view factors based on like standard geometries that we have, or finding all the geometries in a system based on one or two geometry that we can find, we need to implement some rules or regulations. There are four that I'm going to write it down, and after that I'm going to describe each of them. First one is reciprocity rule. The second one is summation rule. The third one is superposition rule, and the fourth one is symmetry rule. We also need to give special attention to self-view factor. Self-view factor. Okay? Why we need those things? As I told you, there are some tables and pictures that we can find view factor for simple or standard geometries. Okay? So of course, if we are facing with the system that one or two of the view factors can be found from the table, what are we going to do with the rest? By applying these rules, we can find the rest of view factors in a system. Or if we are facing with non-standard geometry that somehow we can relate it to the standard geometry, first we can find that standard geometry from the table, we can find the view factor, and after that, by applying these rules, we can get the view factor that we want. Okay? So, but first let me find some kind of general expression for a view factor in terms of differential areas, and after that we can try to prove the reciprocity rule. Okay. Look at this picture. You can see two surfaces of A1 and A2, and you can see the small differential area on each of them, dA1 on surface A1 and dA2 on surface A2. These the distance between these two differential areas is R. In order to find the view factor, we need to find two rates. I'm going to just write those ones. First, the rate at which radiation leaves dA1 and it is intercepted by dA2. So that's the first rate that we need to find. The second rate is the total rate at which radiation leaves dA1 in all directions. Okay, so if we give enough attention to the definition of view factor, we define the view factor as the fraction of radiation leaving surface I that strikes surface J. So in order to find the view factor, we need to find these two rates. First, the rate at which radiation leaves dA1 and it is intercepted by the dA2, and the second one, the total rate at which radiation leaves dA1 in all directions. So I just call this one rate 1 and rate 2. Okay, so let's start with rate 1. We just want to find rate 1, which is the rate at which radiation leaves dA1 and it is intercepted by dA2. If you remember from previous lectures, by applying the radiation intensity concept, we can say that Q dot dA1 to dA2 can be defined as ER sine theta 1 dA1 d omega to 1, and you remember that d omega to 1 is the differential view solid angle to 1 is equal to dA2 cosine T2 theta 2 divided by R2. Then we have 1 to dA2 is equal to E plus R sine theta 1 cosine theta 2 divided by R2 dA1 dA2. Okay, that is the rate 1. For rate 2, what was the rate 2? The total rate at which radiation leaves dA1 in all directions. So radiation that leaves the surface in all directions has the meaning of radiosity in it. All the radiation that leaves the surface. So we can easily say that the Q dot dA1 is equal to 1, all the radiation leaves surface 1 in all direction, dA1, which is pi I plus R dA1. Okay, so now we have both rates. We can define the differential view factor as df dA1 to dA2 is equal to q dot dA1 to dA2 divided by q dot dA1. So it will be equal to cosine theta 1 cosine theta 2 r pi r2 dA2. So differential on dA2. That's the differential view factor. Of course, if we want to find it, we need to do the integration for all the A2. Okay, so we don't want to calculate it, but here I just want to try to show or prove the reciprocity rule. So based on the differential format, I can say that f1 to 2 will be q dot a1 to a2 divided by q dot a1. I'm not going to use the differential format anymore. So the q dot a1 to a2 was a1 a2 e plus r cosine theta 1 cosine theta 2 r2 dA2 dA1, and q dot a1 equal to a1 p I e r dA1 is equal to pi e plus r a1. So f1 to 2 is equal to 1 a1 double integration a1 a2 sine theta 1 cosine theta 2 divided by r2 dA2 dA1. Okay, so if I want to rewrite it, we can say that f1 2 is 1 divided by a1 a2 sine theta 1 cosine theta 2 divided by pi r2 dA2 dA1. Okay, I think previously I forgot to write the pi here. Pi r2. Okay, so we have this. I can say that, okay, let's assume that this double integral is C. Okay, just like keep it. Now we have calculated f1 2. Let me calculate f2 1 as well. So from the definition of view factor, I can say that it's q dot a2 to a1 divided by q dot a2. Q dot a2 to a1 is equal to integration of 2 a1 e plus r cosine theta 1 cosine theta 2 r2 dA1 dA2. Q dot a2 is equal to a2 pi er dA2, which is equal to pi e plus r a2. Okay, so f21 will be equal to 1 a2 divided by a2 a1 cosine theta 1, cosine theta 2, pi r2, dA1, dA2. If you look at this double integration, is exactly the same as the first one, which I mentioned is C, so this one is C as well. Next one we can write it F1 to 2 is equal to CA1, and F2 to 1 is CA2. So from these two we can say that A1 F12 is equal to A2 F21. That's the reciprocity rule. Okay. So we are done with one of the rules. The second one, it's very simple one, the summation rule. Summation rule basically, if you want to show it as a mathematical expression, can be written as this one. We will speak about it later when we are speak about the enclosure with n surfaces, but for now just accept it that the summation rule is saying that all the view factors from one surface to other surfaces are, if we add them, will be equal to 1. But let's see if it really does make any sense for you. For example, I have like a surface, I call it surface 1, for example. So radiation goes out to different surfaces. I don't care how many surfaces are around, but those surfaces will get all the radiation that goes out of 1. Okay? So basically, what fraction of the radiation leaving surface 1 is strike to the areas that I just mentioned? All of that. So 100%. So all the view factors associated with surface 1 will be equal to 1. For example, let's say it's a three surfaces. So 1, 2, 3, 4. So it will be F12 plus F11 plus F13 plus F14 is equal to 1. Why? Because all those 4 surfaces covering all the radiation leaving surface 1. What if it's just like we have just 2 surfaces, 2, 3, so it will be F11 plus F12 plus F13 is equal to 1. If it's 5, again the same story. Okay? But we are going to speak about it when I speak about the enclosure with n surfaces. If you remember, I told you that beside those rules we need to give special attention to the self-view factors. Self-view factors, basically we have 3 different kind of surfaces based on their geometry. The surfaces are either plane, convex, or concave. For plane surface and convex surfaces, we see that the self-view factors are equal to 0. Why? Because no radiation can go back to the surface itself. Okay? So all the radiation leaves the plane surface and convex surface, and that's the reason why the self-view factor of these 2 surfaces are equal to 0. But for concave surface, the self-view factor is not 0. Why? Because it might strike and you see that some of the radiation leaving surface 3 might strike again to the surface 3. So that's a reason why for concave surfaces the self-view factor is not 0. Okay, now we have two important rules or general rules. We have reciprocity, we have summation, and we have like a good understanding of a self-view view factors. Now let's try to solve one example and see how we can put everything together. In this picture shows one enclosure formed by two concentric spheres. We want to find view factors. How many view factors we have here? 4 view factors, and we want to find them. Okay, so let's start with surface 1. Surface 1, what kind of surface it is? It's convex surface. So easily we can say F11 is equal to 0. Okay, by using summation rule we can say that F11 plus F21 is equal to 1. So we know that this one is 0, then F21 is equal to 1. So it was very simple. Immediately we find 2 of the view factors. Now let's go back to the surface 2. Surface 2, what kind of surface the surface 2 is compared to the surface 1? Is concave. So F22 is not 0. But we know that from the summation rule F21 plus F22 is equal to 1, but we can't find any of them to use this summation rule. That's the place that we can use reciprocity. So A1, F2, sorry, I made a mistake here, is A12, it's not A21. It's 1, 2, 1, 2, 1, 2 plus is equal to A2, F21. Okay, so then say that F21 is equal to A1, A2, and F22 is equal to 1 minus A1, A2. Okay, so now you see that we found all the 4 view factors by applying summation rule, reciprocity, as well as self-view factor. Okay. Now let's go back, because I told you that I'm going to speak about about this enclosure with n surfaces. The summation rule, look at this picture. Okay, we have an enclosure with n surfaces, and all the surfaces are radiatively active. The summation rule follows from the conservation requirements that all the radiation leaving surface I, for example, or surface 1, whatever, must be intercepted by the enclosure surface, because there is no other way. So when the radiation goes out of surface I, needs to be absorbed by all those surfaces together. Okay, therefore the sum of the view factors from surface I of an enclosure to all surfaces of the enclosure, including to itself, must be equal to 1. So we can say that the summation rule has been proved. J1 to n is equal to Fij is equal to 1. Okay. But to calculate radiation exchange in an enclosure with n surfaces, let's see how many view factors we need to calculate. We have an enclosure n surfaces. How many view factors we have? N to the power of 2 view factors. N of these view factors can be calculated from summation. Why? Because we have n surfaces and we can write n equations like view factor f11 plus f12 plus f1n is equal to 1, and we can continue fn1 plus fn2 fnn is equal to 1. So we have n equations like that. So n out of n2 view factors can be found from summation rule. N to n minus 1 divided by 2 can be calculated from reciprocity. So basically what is left is n minus 1. So if we have this number of view factors known for us, we can find the rest by using either reciprocity or summation. But now how we can find it? Either from the standard geometry from the tables or pictures, or by using the SelfView Factors. Okay, let's go back to our example and see how does it work. So how many surfaces we have? N is equal to 2. Then we have 4 view factors. Out of these 4, n coming from summation, so 2 can be calculated from summation. One divided by 2, which is 1, coming from reciprocity, minus 1 is equal to 1, so we should have 1 view factor. So if we have, in this special case, if we have just 1 view factor, we can find all the rest. Okay, let's see. For in this case, if you remember, we started with f11, which was a self-view factor. We said that, okay, f11 is 0, so we found 1. Good. Now applying summation rule for the first time, so we find f12 is equal to 1. After that, we applied once reciprocity, just once. We find f21, and again we applied summation rule for the second time, and we find f22. Okay, so we had 1, we applied summation rule, we found the second one, we applied reciprocity, we find the third one, we applied summation rule, we found the fourth one. Sometimes to the start point you need to use a self-view factor. Sometimes it's like from the table that you can go and calculate. Okay, now we talked about reciprocity, we talked about summation, we saw one example. Now it's time to speak about superposition and symmetry rule. Okay? So let's go to this slide and talk about it. Superposition rule. Sometimes we face with surfaces that we cannot find their view factors from standard charts or tables due to their geometry. So their geometry is complicated, we can't find it. What are we supposed to do in those cases? In those cases, the best will be finding the view factor associated with those surfaces through geometries that we know their view factor. Okay, so we need to see that, okay, how we can incorporate the standard geometries that we know or it's easy to find from the table in order to find the view factors of non-standard geometry. Okay, superposition rule can be defined as the view factor from a surface I. Let's say this surface 1 is I and the whole surface of 2 and 3 is J. Okay, so we can say that J1 here and J2 between 2 and 3. Okay, so the superposition rule can be defined as the view factor from a surface I to a surface J is equal, so Fij is equal to the sum of the view factors from surface I to the parts of surface J. So it's equal to Fij1 plus Fij2. But of course it's not just two surfaces, it can be extended. So Fij is equal to I sigma j from 1 to n Fij n. So Fij can be equal to Fij1 plus Fij2 plus Fij3 plus Fij4 or anything. Okay, but look at that like example that we are dealing with. Let's just like this example that we are dealing with. If we apply this superposition rule to this figure, we can say that F1 to 2, 3, both of them surfaces, is equal to F1 to 2 plus F1 to 3. F1, 3, if you look at the picture, F1 to 3 cannot be calculated from any standard chart or table. So that's the reason we can use superposition rule easily. We can say that, okay, F13 is not a standard, we can't find it, but we know that due to superposition rule, we can say that F13 is equal to F1 to 2, 3 triangle easily minus F1 to 2 another triangle easily. Okay, so we found the view factor of a non-standard geometry by using superposition rule and two standard view factor of triangle easily. Okay, that's it. And there is just one more rule left, which is symmetry rule. Symmetry rule. Basically the symmetry rule, we can say that is if surface J and K are symmetric about the surface I, so if surfaces of J and K are symmetric about surface I, then we can say that Fij is equal to Fik. If we apply it to the picture that we can see, because it's symmetric, so we can say that F12 is equal to F13. Okay, now we defined all the rules necessary for this chapter. We also talked about SelfView factors. Let's speak about Crossstring method and see how we can work it out. Okay. Look at this figure. This is the figure 13.16 of our textbook. Let's try to see if we can find F122. Okay, how we can find it? In order to find this view factor, you see that it's not a standard geometry. We can just find. We can't just go to a table or figure and find the view factor. To sort the problem out with those kind of geometries, H.C. Hotel proposed a method called Crossstring Method. String method. So basically, this method is saying that Fij is equal to sigma all the crossed strings minus sigma uncrossed strings divided by 2 multiplied by a string on surface I. If we want to apply it for F12, so F122, let's apply this cross-string method and see how we can find the view factor. So 2 multiplied by a string on surface I. So 1, 2, ij, 2, L1. Crossed string, because we want to find this to that, so crossed string. L6, L5. So L5 plus L6 minus uncrossed strings. L3, L4. Okay, so L1, which is a string and surface I, 2 crossed string, L5, L6, 2 uncrossed string, L3, L4. If we apply the same equation to F221, we can easily find that it will be 2L2, L5 plus L6 minus L3 plus L4. Why? Because the cross string and uncrossed strings are the same. Okay. Now let's look at example 13.5 of our textbook and see if we can find the view factors. Okay. 2 infinity long parallel plates. We have A is equal to 12 centimeter, B is equal to 5 centimeter, and C is equal to 6 centimeter. The question is asking determine the view factor F12 from surface 1 to surface B by using the cross-string method. Okay, so what is asking us to find the view factor by using cross-string method. Okay, cross-string method. So F12 by using cross-string method to L1, 1 to 2 crossed L5 plus L6 minus L3 plus L4. Okay, so L1 is 12 centimeter, L3 is 6 centimeter. What we need to find L4, L5 and L6. Okay, L5 can be easily found. L5 will be 2 is equal to 7.81. L4 is equal to 9.22, and L6 is equal to 13.42. Okay, we just like put the numbers into the correlation, and we will have F12 is equal to 2 divided by 12, 7.81 plus 13.42 minus 6 plus 9.22 is equal to 0.25. So F12 is equal to 0.25. That was the section A of the example. In section B is saying that derive the cross-string formula by forming triangles on the given geometry and using equation 13.15 for view factors between the side of triangles. Okay, so if we go to the table 13.2, we see that there is a correlation how to find view factors for a three-sided enclosure. Okay, if we want to apply this one into the example, easily we can say that, okay, we have two triangles, so A, B, C, and the other one I can say that it's more or less A, B, D. So this is surface 1, this is surface 1, this is surface 3, this is surface 6, this is surface 4, and this is surface 5. Okay, so let's apply this correlation. So F1 to 3 for this triangle, I can say that, okay, it's 2L1 L1 plus L3 minus L6. F1 to 4 is equal to 2L1 L1 plus L4 minus L5. Okay, so easily I found these two view factors. So F13, I just write it here, 2L1 L1 plus L3 minus L6. F14 is equal to L1 plus L4 minus L5 divided by 2L1. But we were interested in F1 to 2. How we are going to find this one? It's easily. We use summation rule. Summation rule, so we say that, okay, F11 plus F12 plus F13 plus F14 is equal to 1. Okay, the surface is plane surface, so F11 is equal to 0, F12 is equal to 1 minus F13 minus 1, 4. So it's equal to 1 minus L1 plus L3 minus L6 to L1 minus L1 plus L4 minus L5 divided by 2L1. So it's equal to 2L1 minus L1 minus L3 plus L6 minus L1 minus L4 plus L5. This will go. So what we have is L5 plus L6 minus L3 plus L4 divided by 2L1. What is it? It is exactly what we got from Crossstring method. So no matter what method you use, the answer will be the same. But of course, using tables and standard geometry can help a lot, but of course you can't just use those tables and figures to find the view factors. You need always to incorporate it into the SelfView factor as well as rules that I told you about, either reciprocity, summation, superposition, or symmetry. Okay, now let's finish this section with an example. It's question 13.14 of our textbook. As you can see here, the question is asking to determine the view factor of f1 and f11 and f12. So a circular cone of diameter d is positioned on a common axis with a circular disk, also with the same diameter, and the distance of L as shown in the figure, with a hypothetical area A3 corresponding to the opening of the cone. Determine the values of f11, f12 if L is equal to D is equal to 100 millimeters. Okay. Let's first do a 2D sketch of what we have. So we have the surface 1, the all surface. We have hypothetical surface of 3, and we have surface 2, which is with the same diameter as surface 3. Okay, 2. So it's the same. Okay. Now we have these three surfaces. What we need to find is f11 and f12. So the question is asking us to find these two view factors. Okay. So first we know that like surfaces of 1 and 3, they create a kind of like an enclosure. Okay. So I can say that summation rule f11 plus f13 is equal to 1. Okay. But can I say anything regarding the self-view factor of 1? Not really. So because I can't say anything about it, I can't find anything, so we just like keep it for now. The only thing that I can do is write f11 as a part of f13. So f11 is equal to 1 minus f13. We didn't do anything, just like put it the other side. If we apply the summation rule for surface 3, we can say that it's f31 plus f33 is equal to 1. Okay? Can we say that f33 is equal to 0? Yes. Why? Because it's a plane surface. So f31 is equal to 1. We found f31, but here is f13. How we can relate these two to each other? Reciprocity. Okay, so based on the reciprocity, we can say that a1 f13 is equal to a3 f31. So f13 is equal to a3 a1 f31 is 1. Okay, so now we need to calculate a3 and a1 and we will be sorted. Okay, a3, what is the surface area of a3? It's a disk, so pi 2 divided by 4. How about a1? It's a cone. Not going to describe it, but you just need to go and find it. That's how you find the area of a cone. L2 plus okay. By applying that, f13 will be pi d2 divided by 4 divided by pi d2 L2. Sorry, because L is equal to D, we can just put it D2 plus 2 divided by 2 to the power of 1, 2. I have calculated that and it's 0.447. Okay, so we have f13 is 0.447, then f11 will be 0.553. So the first part of the question sorted, we find f11. The second part is asking if we can find f12. Okay, so we want to find f12. Let's apply reciprocity. Say that okay, a1 f12 it's equal to a2 f21. Okay, so a1 f12 is equal to a2 a1 f21. So again a2 is equal to a3. Why? Because both of them, they are just a disk, so pi d2 divided by 4, and a1, which is the cone, it's 5 d2 pi divided by 4. Okay, so we have those two. If we put it into the correlation, we will find f12 is equal to f21 divided by radical 5. Okay, so but how we can find f21, because for f12 first we need to find f21 and after that divided by 5. Okay, let me just like sketch the 2D. So we had this one is, this is 3 and this is surface 2. If you go to table 13.1 of the textbook, you can see that there is one correlation to calculate the view factor between two coaxial parallel disks. So surface 2 and surface 3, they are coaxial parallel disks, so we can find F23 based on the correlation that you can find from table 13.1. I'm not going to write it, but 2.3 is equal to 0.1716. Please go to your textbook and see if you can find the right correlation for coaxial parallel disks. Okay, now we have view factor between surface 2 and 3, but here we need the view factor between surface 2 and surface 1. How we are going to sort it out? So let me just write it down. So F12, it's F21, and we have F23 is equal to 0.1716. So we want to find it. But if you look at this figure 1, 3, and 2, F2 to 3 is equal to F2 to 1. Okay, let me explain to you how. We have a surface 2. Let's say radiation is going out of this surface. Okay, because surface 3 works as like a gate for surface 1, all the radiation leaving surface 2 striking to surface 3 will strike to surface 1 as well. So definition of view factor, the fraction of the radiation leaving surface 2 that strikes to surface 3 is exactly the same as the fraction of radiation leaving surface 2 that strikes surface 3. Because we know that the surface 3 is a hypothetical surface, so it's not a real surface. All the rays of radiation that goes through the gate of 3 finally will strike to surface 1. That's the reason why view factor of 2 to 3 is the same as view factor of 2 to 1. So now it's easy. F12 is equal to 0.1716 divided by radical 5 is equal to 0.0767. Okay, thank you for your attention. That was the end of our 4th lecture. Please go through your textbook, read it, and go through the lecture. If you have any a question, if you don't understand the section, please go and play the video one more time. Go to your textbook. If you can't find the information or you feel that it's very difficult for you to understand, you are more than welcome to drop me an email and I try to get back to you as soon as possible. But please go through the textbook first, play the lecture one more time, and after that, if you don't understand, contact me. Try to push yourself to understand. I try to describe it as simple as possible, but of course not all the time can be effective and you might have some questions. You are more than welcome to drop me an email, but because it's a video lecture, you can review it many times, 2 times, 3 times, and after that you can go to your textbook. You can open the textbook in front of your computer or laptop, go through the video, stop the video, and see if you can find the relative information in your textbook, and try to do all the examples again based on the procedure that I explained in the video, and you will be fine.